Okay, today's talk will be given by Dr. Arthur Suvorov. He's currently a Humboldt Fellow in the Theoretical Astrophysics Research Group at the University of Tübingen in Germany, where he's collaborating with Professor Dr. Kostas Kokutas. Arthur Suvorov obtained his PhD at the University of Melbourne under the supervision of Andrew Melatos in 2018. He there won numerous awards and prizes, including Albert Schimming Award, Karl Moppert Award, A.J. Gutman Prize, and Reuter Prize. After the PhD, he took a detour from astrophysics to work at the RMIT, also in Melbourne, on problems in sensor design and information theory through a grant funded by the US Air Force Office of Scientific Research. And after this detour from astrophysics, he moved to his current position in Tübingen since mid-2019. Dr. Suvorov's research is on matters of high-energy astrophysics, including astrophysics of neutron stars, magnetars, and astroseismology, and black hole perturbation theory. And more specifically, in his PhD thesis on neutron star physics and some aspects of modified gravity. So today is going to talk to us about one of his latest works, building a theory of gravity around a given spacetime. We'll let him speak for 45 minutes, and then there will be a 15 minutes time for questions. So Arthur, you can unmute yourself, share the screen, and start whenever you want.
Okay, great. Thank you very much for that nice introduction. It's a great pleasure to be here. And by here, I mean, of course, in my own office. But nevertheless, it's, you know, I appreciate the invitation all the same. We do the best we can in the times we have. So thank you. So indeed, I'm going to be talking about some aspects of what might be called the inverse problem in gravity in some kind of general sense. And I'll lead you through exactly what that means and what I intend to show you some new results as well as some old results about this particular study. So, you know, in general relativity, you know, black holes present one of the best objects to test the high energy regime with, given they are somehow the most extreme objects with the strongest gravitational fields, therefore is the place you might find high energy corrections. So in GR, there are a slew of uniqueness results, essentially, which culminate in the so-called Kerr hypothesis, which states basically that astrophysically stable black holes are uniquely represented by the kermetric. I emphasize the astrophysically stable point, which is sometimes left off of these theorems, because really they are mathematical results that involve various assumptions about the stress energy and about the symmetries of space-time and so on. Which might not necessarily apply in a realistic astrophysical environment. So for example, if I had a black hole is not a lone object in a universe that is otherwise devoid of matter. It might have a disk around it, various other things, for example, in a globular cluster. It could be some other bodies interacting. And so the space-time might look like a superposition of Kerr plus some extra pieces. But really, in a variety of environments and scenarios, the Kerr aspect dominates, or you would expect it to dominate at least, and therefore when you're testing for space-time properties using various experiments, you really are looking at the Kerr or non-Kerr nature of things. And in particular, a non-Kerr signature would signify very strongly that you have some kind of smoking gun for non-general relativity, right, because of these uniqueness theorems. So various recent experiments and even not so recent experiments that come from the electromagnetic sector, for example, X-ray reflection spectroscopy, when you look at particle emission and reflections around accretion disks in microquasars or in supermassive systems, or quasi-oscillations, which might be tied to the epicyclic frequencies of the space-time geometry with modes that get trapped or other behaviors, fluid behaviors in disks around black holes. And on the other side, there's of course the gravitational wave sector, which has recently become available in the experimental side. Looking at tests of inspirals and so forth. There's no strong evidence, at least, for the breakdown of general relativity from any of these experiments. Now, that isn't to say that this necessarily points to general relativity. It's just saying that the data is consistent and validates the Kerr hypothesis. But in particular, there is some room for modified gravity parameters to be non-zero. And there's theoretical reasons to suspect, in fact, that general relativity does break down in some respects. So one I like to think of just as an example is what you might call a singularity problem, that black holes in the classical GR inevitably form singularities due to these Hawking-Penrose theorems and so forth. And so if I have a merger of two black holes, I've now gone from a universe essentially that has two holes in it, or two ring holes based on the properties, right, the singularities of the objects, that then get moved into one hole in the merger remnant, right? I've somehow fundamentally altered the topological properties of space-time in a purely classical sense when I look at this in GR. And this is kind of problematic and very extreme, and I don't think anybody seriously expects that this happens, for example. So aside from the fact that GR does not predict or does not claim to make predictions in the vicinity of singularities, there is, some very strong physical sense that there should be something different potentially happening there, and there should be some kind of effects that resolve this. So with these kind of ideas in mind, there's a great deal of interest in trying to classify and find black hole solutions in modified theories, and to see how they might influence the electromagnetic or gravitational wave signatures that we may be able to find at some point. So the question then becomes, more or less, well, suppose we did in fact find some non-Kerr features in the geometry, right? If we found some evidence that the kermetric, which has two unique parameters only, the mass and the spin uniquely describe that object in GR, if we found some third or fourth parameters that were strongly centered around non-zero values, this would provide some evidence for non-GR, but it doesn't necessarily tell us what theory it is we're looking at, right? And so the question is, how can we use that information of not a null detection, but a positive detection for non-Kerr features in some kind of generic way to guide us towards what you might call the true theory of gravity. So the same question applies for cosmology as well, which I'll talk a little bit about as we go on too. Some people believe, for example, that the Hubble tension that exists points to new physics, the ultraviolet scale, for example. That's very subjective, whether or not you agree with that, but nevertheless, even away from black holes on the other end of the extreme, when you move to very large distances as opposed to very short distances, maybe there's some new physics too. So, there's this kind of problem of reconstructing what the theory might be based on the observables. This kind of generally falls into this inverse problem category, which is, this cartoon on the left is kind of very loosely showing you here. So the forward problem is essentially, I guess what you might call the natural, or at least natural from a theoretician's viewpoint, not necessarily experimentalist viewpoint, that you start with some kind of model and you look for solutions in that model, for example, black hole solutions within that theory, and try to then find what the signatures of such an object might be. There are a number of difficulties associated with doing this. The field equations in GR themselves are very complicated already. When you start moving to different theories, the complexity only increases as a rule. So the differential equations are highly nonlinear in some meaningful way, and even often higher than second order if you have some kind of absence of a Lovelock type theorem and so on. So classifying the solutions within that theory is very difficult. And furthermore, the inverse problem can also be very difficult, right? If I'm starting from some particular field configuration, so going in the opposite direction, where instead of now starting with the action, I start with the metric, for example, and I try to say, well, what theories might give rise to this black hole arising as a solution? If I found some particular favorite non-Kerr model of mine was an exact solution, right? Or rather, would fit the data well, thereby suggesting that it ought to be an exact solution in whatever theory of gravity governs nature, then I would like to try to figure out what the theory is, and this can be very difficult because of this. You're now trying to sort of invert nonlinear operators in some meaningful sense. So this can be very difficult in general. I'd just like to, before moving on to more technical details about the particulars of what the inverse problem is and how people have approached this in gravity, starting from a metric, trying to find the action, I like to give one example of this so-called cosmological reconstruction, and I'll give a black hole example in a little bit too. In the F of R theories, which are a particular favorite theory of mine, for whatever reason, I guess, though these particular theories will play a role later on in the talk. There's a particular reason I'm choosing this one at the moment. So what these theories are, if you haven't met them before, is there's some kind of non-linear generalization of GR. And when I say non-linear, I mean non-linear at the level of the action, not in the equations. Okay, so general relativity, the field equations are derived from the Einstein-Hilbert-Lagrangian, or action, which consists of the Ricci scalar and maybe some constant, cosmological constant, if you're into that. And so therefore, the question is, well, why is it necessarily only the linear order terms, right? You could imagine there could be some quadratic corrections, or more generally, some kind of higher order corrections that come in the form of a function in the action. So hence this not very creative but pragmatic name of F of R theories, where the constant, where the linear Ricci scalar in the action is replaced by some function of that quantity. So they've been introduced for a variety of reasons, which I won't really go into, but nevertheless, the equations look something like this. And they have an interesting feature that GR does not. So the equations look relatively similar, but you notice there's this function f that floats around, and its derivative that floats around in the equations of motion here on the left-hand side. And so we have an extra freedom here in this theory that's not present in GR. In particular, the metric tensor is the dynamical variable still, but we have some freedom in how we want to choose this function f, right? So in principle, you're trying to constrain what f might look like. And if you could find through data, for example, that it had to look like a linear term, then you would essentially validate GR as a particular class of the F of R theories. But because you have this extra freedom at the level of the action, there's some extra interesting things that you can do with this. So in particular, as I said, just in cosmology, so these FLRW cosmologies, sometimes just called Friedman, Robertson, Walker. I don't know why poor old Lemaitre misses out on having his name attached to this sometimes. But in any case, this just represents a homogeneous isotropic cosmology, the simplest, essentially, cosmological model that you might expect to have. So by virtue of having homogeneity and isotropicity, you kill off the spatial dependencies in the metric, and all you are left with is some kind of time dependence in some kind of meaningful invariant way. So you have a scale factor, which is this function A, which essentially determines the expansion rate of the universe, as proportional to the matter density or radiation or what have you that comes from the fluid. This is this rho piece at the end here. So the point is that since the metric only depends on time, in this particular case, the curvature invariants of the space-time only depend on time also. So the Ricci scalar, which is relevant for F of R theories especially, is only a function of time, right? In this, I guess what you might call the third line I've written here, right? It's a function of the Hubble parameter, which depends on the scale factor. I haven't shown you what the metric is here, but hopefully you're all reasonably familiar with this kind of simple cosmological model. And so because the Ricci scalar only depends on time here, the field equations therefore only have this kind of one dependable coordinate. And so what that means is I can essentially invert this equation, which I have here, which is equation 1 here. I can invert this for some particular Hubble parameter that I wanted for the function f, right? So f is a function of r, which is a function of t. So this is some sense of free function at the level of the action that I wanted to pick. So at the very least, I can trade in one of my metric degrees of freedom for an action degree of freedom, if you want to think about it like that. So I could invert this if I had observations that told me the scale factor had to be exactly this for whatever reason, imagine, right? Then I could invert this to say this is what the f has to look like in order for that theory to match data. And so in this way, f is tuned in such a way that you can produce some particular cosmological evolution. So this is a solution to the inverse problem in this very simple case in F of R gravities, right? Where I've traded some kind of experimental thing, let's say A or H, depending on which one, you know, they're the same thing, but I've traded that for some kind of action variable, this function f. So I'll now move into kind of black holes, which has a similar story to that, and I'll show you very soon exactly how that all fits together, at least in the F of R case. But I want to just introduce some terminology very quickly. It's not my favorite terminology, but this is very commonly used in the literature, so I think it's important to introduce it, is that the forward problem in this kind of black hole case, where I'm trying to then figure out if it's Kerr or not Kerr based on data, the forward attack is called the top-down, right? So I pick some particular theory of gravity and I compare the solutions obtained with some suitable GR counterpart, in this case, the kermetric, right? So I take some f of r theory, for example, with some quadratic corrections or whatever you like, and I try to look at what are the black holes within that theory and match them to the data. As I said before, this is very difficult because of this problem of finding and classifying exact solutions. So therefore, we have the so-called bottom-up approach has been introduced to kind of remedy this problem that finding exact solutions can be very difficult. And this is an approach where rather than saying I want to have some kind of particulars in the action, I want to have some particulars in the metric, right? No matter what theory of gravity I have, black holes should be relatively Kerr, right? Not exactly maybe, but you know, maybe there are some fundamental properties, symmetries that I'd like to preserve for black holes, and I'm not willing to give them up. In that case, I pick some particular phenomenological parameterization of the spacetime and try to see what the predictions for this might be. So I pick a metric divorced from a theory in order to figure out and use that pragmatically to try to discern some properties of the geometry. So this is really the forward versus inverse problem, and in particular this lingo for this black hole tests, right? And so even if the deviation parameters of my parameterized metric that's non-Kerr in some way, right? It has some number that's not the mass or angular momentum in it that describes it that I need in order to describe it, or several numbers. This does not necessarily point you towards the true theory of gravity, right? I just say, well, it looks like a non-Kerr object that has these properties, but what exactly is that teaching us, right? So the bottom-up approaches, although they're very useful, right, pragmatically speaking, in order to actually put constraints on the nature of theories and so forth, they are essentially inconsistent mathematically to some degree, right? And this depends on exactly what kind of experiment you're trying to do, the degree to how serious this may or may not be. So, you know, back reaction effects, for example, if I have some radiation from a system, that means there's some kind of energy loss that's coming from there. And therefore, there needs to be some way in which the space-time back reacts in order to account for this energy loss in a totally self-consistent way, right? So for electromagnetic experiments that I talked a little bit about before, this is really often unimportant. So the back reactions might primarily behave in the fluid sector rather than in the gravitational sector in some meaningful way, right? And therefore, I'm pretty sure that the back reactions are negligible. And so even if they might be there in principle, I'm never going to be able to detect them, even if I do it self-consistently or not. For gravitational waves, it's less obvious that this is allowed, right? Because they are directly tied to the particulars of the field equations, right? The gravitational waves are, at least mathematically, a perturbation in the metric. And therefore, in order to actually study what the perturbation is, I have to have some equations of motion. So there are some clever ways that you can parameterize this, that we have some experts in the audience that know far more about this than I do. But nevertheless, you know, it's not entirely obvious to what extent you can account for this. So there's value in attaching a theory to some particular parameterization, more than just trying to learn about the actual behavior of nature, if you will, if you want to think about it like that, but also to actually self-consistently build on these approaches. So just quickly, I will talk about developments now, I guess a historical account of the inverse problem to some degree for black holes. And then I'll get into the actual new work in short order. So in the case of the cosmological reconstruction in F of R theories, you can do a very similar thing here for static black holes, right? So if we have a static black hole in these Boyer-Linguist or equivalent coordinates, the metric is usually written like this that I have here on the screen. Right, so I've killed off all the spatial dependence except for the radius, and I've killed off time, assuming that there's some kind of Birkhoff theorem that applies here. And therefore, my black hole is only described by some two free functions that depend only on the radius, some kind of areal radius for my space-time. And so what that means is, in much the same way that I had for the cosmological case, because I have only one coordinate, essentially, that everything depends on, I can invert the field equations for F in some kind of straightforward or relatively straightforward way, right? So I have three ignorable coordinates, which is in this case the two angles and time for the static black holes, or the three spatial coordinates in the case of the homogeneous and isotropic cosmology. And therefore, you can write down all the field equations and show, in fact, that you can rewrite one of the metric functions, right? I've traded in one of the metric degrees of freedom for one of the actional degrees of freedom, in this case, the F and B, right? So I'm just going to go back very quickly and remind you that B here is this GRR component, right? It's the R radial component of the metric in this diagonal representation, this Boyer-Linguist coordinates. So I can represent this function B in some special way that involves this function F and invert that, right? So I can essentially say, well, if I'm willing to have some different function A, right, I can pick whatever B I like and find an F of R theory around that. The configuration space of the F of R theories is large enough that I can accommodate any particular metric function B that I so choose for some F, right? So these Fs that might give rise to whatever B you're interested in might not necessarily agree with other astrophysical constraints, right? There are solar system constraints that you have to deal with beyond just that of black holes. And so I'll get to that a bit later on. But nevertheless, this hopefully demonstrates to you this kind of the straightforward idea of doing this for static black holes, at least, that you can invert and trade one of your freedoms in the action to the metric. So what goes wrong here when we have a more realistic space-time? In stationary spacetimes, for example, where we have some off-diagonal components, we have a rotating geometry. So there's a mass and angular momentum and maybe something else. We have more than 3 ignorable coordinates, and therefore you can't play this same trick that we had before on this previous slide. Sorry, I'm going to dart back again here. The Ricci scalar has to depend essentially on R and theta, right? In some particular way, if I have these only 2 ignorable coordinates rather than 3, I have stationary axis symmetry, but not staticity, right? Then because there's a degeneracy here and that the Ricci scalar depends on R and theta, I might not be able to invert this function F in general, right? Because I depend on 2 coordinates, whereas I have just one function, essentially, right? So the degree of freedoms in there are higher than what I have available to me in order to try to constrain this thing. So in more general cases where I have stationarity, or if I have a cosmology that is not purely homogeneous or isotropic, maybe I have a vorticity or whatever you like within there. There could be some complicated things that we expect in reality that prevent you from doing this. So how do we move forward from this to a more general case, and how is this all connected to some kind of general solution here? Well, if we have some particular R, let's say, what we can observe from the F of R field equations also is that if this function F vanishes at whatever point this R is, and its derivative vanishes at that point, then the field equations will also be satisfied. So we could do this kind of maximally symmetric case, and we can also do this case where the Ricci scalar is constant too, right? So this condition that F equals F prime equals 0 has some dubious physical properties, like the existence of ghosts and things like that, which I, again, will hopefully talk about towards the end given time. But mathematically, at least, there is a means that I can build a theory, an F of R theory around whatever space-time I like, provided that the Ricci scalar is constant. So in particular, if I have this functional form down at the bottom here, so I have whatever space-time that has some constant scalar curvature, which is quite a restrictive constraint, obviously, but nevertheless imagine that I had some other general thing that had some constant scalar curvature, then I can find this kind of very general class of F of R theories for which that metric is an exact solution. So in the maximally symmetric case, I could do this direct inversion to try to solve the inverse problem. Or if I have some very particular space-time that has some special properties like a constant scalar curvature, I can also solve the inverse problem in this way, right? And build some kind of general Taylor series of F such that this particular property of F equals F prime is 0. So there's some interesting tricks, I guess, that you can then use to try to generalize this approach and say, well, how can we use the fact that, that if I have a constant scalar curvature, I have a way to build a theory around that. And so this enters the so-called Theyamabay problem, which, mathematicians and physicists call this thing a different things. I'll try to use the physics language as much as possible. So the idea being that I take a frame transformation of my metric, or a conformal mapping. So the metric, as it's usually written in this kind of general way that I've shown you before, goes under the heading of Jordan frame. But I can also map to some kind of conformal frame in this mapping here that's shown you in this first sentence. or the second sentence, where I introduce some kind of conformal scaling. So what this means is I change my clocks and meters and how they represent space and time by some function in space, right? So I have some function that scales all of my clocks and rulers that floats around here, and I've essentially mapped into some different frame. And so this is also just some conformal mapping, but mathematically speaking, I can connect the scalar curvature in the conformal frame to the scalar curvature in the ordinary or Jordan frame, right? So I'm sorry if this is a little bit abstract. I hope at least, you know, this idea of a conformal mapping is used often to simplify equations, right? It's just a means, especially in scalar tensor theory. This is where this is very often used, is a technique to essentially simplify the dynamics of the system. So I can pick some conformal factor that makes my equations look nicer, especially for the use of numerical solution. This can be very useful, and then transform the frame back. But anyway, from the mathematical standpoint, there is a relationship between the scalar curvature in the conformal frame and the Jordan frame, which is given by this equation here. So I have this Laplace-Beltrami operator, which is just like the Laplacian with some curvature in it, and some derivatives of that. And so the Theyamabay problem is kind of a relatively famous, I guess you might say, mathematical problem that says, well, does there exist a solution to this such that R tilde is constant, right? Can I pick some frame of reference such that my scalar curvature in that frame is constant? And so this is known to be true in a number of cases, that there exists a solution to this so-called Theyamabay problem, that there is a particular frame I can pick such that the scalar curvature is constant. So what does that mean from this perspective of what we just talked about a minute ago? Well, that means that because whenever the scalar curvature is constant, I can find an f of r theory such that I have an exact solution, right? What that means is that if there's a solution to the Theyamabay problem, I can also find a solution to the inverse problem in that conformal frame. So that's a bit of a mouthful, I guess, to think about, but nevertheless represents kind of the first steps in a kind of general solution to the inverse problem. There are some issues here, physically speaking, whether or not these two frames are physically equivalent is kind of an active debate that's going on in the literature. So we'd like to develop a method that doesn't involve mapping between frames. But this at least proves, for example, some interesting aspects about the configuration space of f of r theories, the allowed solution space. For example, practically any conceivable null cone structure can arise in some f of r theory, right? Because if I took whatever metric you like, right, some arbitrary metric, provided that a solution to the Theyamabay problem exists, such that this r tilde is constant, I therefore can build a theory around that, such that that metric is an exact solution, right? Because the scalar curvature is then constant. And then I can map back between frames. And so null cones, right, being null, are immune essentially to conformal mappings. And so what that means is I can then build any kind of null cone structure that I like here. Just as an example, it's not necessarily relevant for black holes, but it's kind of to lead you through the thinking, I guess, for how we move forward in this. So with these previous concepts in mind, I'm now going to finally get to the punchlines of this talk. We can consider I've put new in with a question mark here because I've done some fairly extensive looking and have not found anyone talk about theories of this form before. But it's totally possible that it exists in some paper I don't know about. So if anybody knows, has met these before, I'd be very interested to hear about that and give proper credit. But nevertheless, what I'm introducing here is some particular action here, which is another kind of new theory, right? So what we have here is very similar to the f of r case, right? We have some free function, little f, that floats around in this action. Now, instead of just having the Ricci scalar by itself, we are coupling this to some scalar field as well, right? So we have this capital F, which is this kind of scale factor that floats around and couples to the scalar curvature. We have some kinetic and potential terms, right? Little omega is related to the kinetic term of the scalar field, and capital V is a potential term. So we have here now a scalar tensor theory rather than being a pure tensor theory. We have introduced a scalar degree of freedom here, as well as a freedom at the level of the action with this little f. So in particular, there are several cases where this theory reduces to some well-known examples. So the case where little f is just linear, we recover exactly scalar tensor theory. Okay, so this is the standard action for scalar tensor theory in the case where little f is linear, sort of very well known. And we also can recover pure f of r gravity, obviously, where we kill off the scalar field, right? If we just have a constant scalar field, we go back to the f of r case. So all of the previous results that I introduced to you about some special cases where we can build solutions to the inverse problem also apply here to this case, right, where we just kill off the scalar field. There's also a curvature coupled modification of this so-called k-essence theory, where usually we have this Ricci scalar and then we have some function of the kinetic and potential terms. So there is some generalizations and modifications, I guess, to known cases that have been kind of introduced here. So what's the point of this theory and why should anybody care about it? Well, you know, the physical nature of it aside, which I will talk a little bit about, you know, this is one particular theory that will have some interesting properties regarding the inverse problem that we'll get to. So you can derive the equations of motion in this theory by essentially just varying the action with respect to the metric and the scalar field in the same way that you do in every other theory. So the equations of motion actually look qualitatively similar to the f of r equations that I showed you before. If you can try to remember what those look like, we have something very similar here with these extra pieces of involving the scalar field and so on, but we have this f, right, and little f and its derivatives that float around in both the scalar field and the metric equations. So the particulars of that aren't super important, but you know, there are some sanity checks that we have to do about this theory before we can even start thinking about using it for anything to describe nature in some meaningful way. So there are several conditions we want to impose here. For example, we want to have that the graviton carries a positive energy. So what that means essentially is that there are no negative energy modes for gravitational waves and things of this sort. You don't want to have ghosts, you don't want to have tachyons, you want to have everything be well behaved in such a way that you don't have any pathological instabilities that can arise. So you want this in particular in the gravitational sector and in the scalar field sector. You don't want the scalar field to carry negative kinetic energies such that then it would want to decay forever and you know, lead to this kind of infinite energy problem. So there are various conditions that you can derive on the theory such that these are preserved. I don't really want to labor too long under these particulars, but you know, nevertheless, there are some kind of inequalities that you want to impose on these functions in general in order to have something be well behaved. So there are various other aspects of these theories. This is just a snapshot of some notes that you know, some calculations that I was doing, not for any particular reason, but just to show you, you know, a feeling for what you're looking at here. So you can do other things to try to test the sanity of the theory. One thing that you often like is to have energy momentum conservation, right? So I have some field equations, and if I have a stress energy tensor that populates the right-hand side of the equations of motion, I also want to ensure that when I take a covariant derivative of the left-hand side, it get exactly zero. And then what this means is that no matter what matter I put into my geometry, it's going to satisfy energy momentum conservation and have a zero divergence. You know, there are some theories where this doesn't happen and they have very interesting physical properties, but nevertheless, this is not one of those examples that any particular little f that you choose, you can prove using the Bianchi identities essentially in the same way that you do in GR, that you have energy momentum conservation exactly in this theory. Okay, so again, I don't really want to talk too much in detail about the physical properties, at least, you know, the sort of generic physical properties of the theory just yet, you know, or ever here at least. But just to give you, those was just to give you a feel that, you know, it's not totally outrageous, these theories at least. So now we get to the actual main result that everyone's been waiting for. And this is that given any metric G, what we can do is we can pick a scalar field such that x equals x naught. Remember, this x here is the particular you know, functional that the action depends on, right? So it's this capital F coupled to the Ricci scalar with the kinetic and potential terms of the scalar field. Okay, so if we can choose the scalar field such that this x is constant and the function little f satisfies this property that it vanishes and its derivative vanishes at one particular point, then G will be a solution to the field equations. So this can kind of be seen here from this bottom equation that we have down here, where again we have f and f prime, right? So every term in this equation depends on f or f prime. And so if for some particular scalar field metric combination, this x happens to be constant, and f and its derivative also vanish at that point, then what you're going to do is you have an exact solution, right? You're going to have, in some sense, a 0 equals 0 situation coming along here. And therefore, regardless of the particulars of your metric G, provided that the scalar field is tuned in such a way that those, those other terms are satisfied, this condition x equals x0, then you will have an exact solution here. So I know that's there's sort of a lot of mathematical results to keep in mind when thinking about that, but I'll go back to that and sort of relate them to various points, hopefully, in the last minutes or however long of this talk. So just to actually go back to what we started with, right? I'm sort of talking about general metrics and solutions of field equations for some f and so on. It's a little bit abstract. So it's useful to actually connect this with a physical problem that we wanted to start with. So let's say I have some particular deformed Kerr spacetime. Okay, so the various authors, even some in this audience, I'm sure, who have looked at these kind of phenomenological parameterizations in this bottom-up approach that I mentioned before. You want to preserve some nice properties of black holes, independently of what theory you're looking at. You want it to be Kerr-like in some meaningful way. And so this equation here, this line element, is one particular example of a deformed Kerr metric. So what we have here is there's this T phi, theta, and so on components, which looks very much like the Kerr metric in Boyer-Linguist coordinates, except we have this little parameter epsilon. Sorry, it's a little bit invisible in the way this is written, but after this equation, we have where delta equals, and you can see there are these Kerr pieces, which is like r squared minus 2mr plus a squared, and then there's this epsilon piece, right? So what this epsilon represents is some kind of extra hair that the spacetime might contain. So this particular deformed Kerr metric, for anyone who cares about this, is one of these particular Konoplia-Retzola-Zdenko metrics, or it was also derived by Johansen, Saltis, and various others. This has appeared in this particular metric, which has a number of very nice properties: existence of horizons, regularity, and so on, all the things that you would expect maybe of a really nice solution. But it has this extra free parameter that is to be constrained by experiment, right? So I want to do some electromagnetic or gravitational wave experiments, and I see there's some epsilon here, and I want to see how can it be different from 0. But even if I found it to be non-zero, I'm not sure exactly how this points to a theory, right? I've just got some kind of metric here. I might be able to say with some certainty that it's not GR, but if I just put constraints on this metric, it's not actually necessarily telling me something about the action, at least not obviously, right? So what can we do here? Well, the main result is essentially, as I showed you before, we're going to play this game of choosing some particular f and choosing some particular scalar field such that that metric is a solution to the equations of motion. So
Arthur?
Yep.
Just for your information, you have 10 minutes left.
Great, thank you.
For the talk. You're welcome.
Thank you. So the mixed scalar f of r, I don't really know what the best way to call this theory is. F of x was a sensible name, but that represents a different kind of theory again. So I've just called it mixed scalar f of r for lack of a better name. So one particular case where this f looks like x to the 1 plus delta is an interesting case of this theory. So what this actually represents is some kind of infinitesimal deviation from scalar tensor geometries. So when you remember, if you remember, we had I showed some examples where this theory reduces to well-known cases. So in the case where f is exactly linear, we recover just good old-fashioned scalar tensor theory. However, now if we have some x to the 1 plus delta, so we have some nonlinearities that float around in the action at some kind of infinitesimal level, for example, right? Some very small aspects there in the action. This can already have very large consequences for the configuration space of the theory in this particular way. So provided that the scalar field solves this kinematic constraint equation, right? This is this equation we had before, essentially that x has to be constant, right? In this case, I've just chosen that particular constant to be 0. So we have this equation where we relate the properties of this, we have the potential and the kinetic terms, and there's the Ricci scalar, right? So the Ricci scalar is fixed for this particular geometry because we want to have this deformed Kerr metric that I showed you as a solution. So now I have an equation essentially for the scalar field, right? This is what this equation is, subject to some conditions on f, v, and omega that I want to pick such that I don't have tachyons and ghosts, right? So there's all these kind of things interplaying here. But nevertheless, I can solve this equation for what the scalar field has to be such that that metric is an exact solution to the theory. Okay, so picking some values of epsilon, right? We can solve that equation. It has to be done numerically as a rule. Unfortunately, there's no way getting around that. The equations are not super complicated, but still require some numerical evaluation. In any case, you could solve them without too much difficulty, and you get profiles that look like this. So what this is a sample of these radial scalar field profiles for some values of epsilon. So in the case that epsilon is exactly 0, we have the Kerr metric. Right, this is just given by this this dashed gray line at the bottom of the graph here. Phi equals 1. Okay, and so there's a sort of general properties of these scalar fields that you can see. They diverge at the horizon for the black hole, right, which is nearly at the Kerr value, but slightly off depending on the value of epsilon. You can see that the lines move a little bit. This is not a problem. You know, this is a property of the coordinate choices. You can check carefully that the curvature and variance don't diverge and things like this. You know, but the line element itself diverges at the horizon because of this choice of coordinates. So the scalar field does too. But otherwise, it decays very, very quickly. Even at 10 Schwarzschild radii here already, any of these curves, -1, 2, or 3, are all very close to the value 1. So this value 1 is exactly the Newtonian value that you need to have in order to satisfy, you know, that you recover Newtonian gravity, essentially, very far away from the source. So what this means is that there is some hair, some scalar hair induced by the, there is some scalar hair that's induced by this parameter epsilon, and that is very short-lived, right? So as soon as you're anything like, you know, a 10 or more Schwarzschild radii away from the black hole, you can't even detect this scalar hair anymore. It's practically invisible. But it would exist in this particular theory such that that metric would then be an exact solution. So there's some kind of well-behaved profile here that you can pick such that things are going well. So it's a little bit quick, but this seems to suggest a couple of things. So first of all, that there is a well-behaved scalar field profile for all values of this deformation parameter that makes sense, right? Such that you don't have naked singularities and things like this, but that there is some choices of this thing such that for this particular x to the 1 plus delta, we have an exact solution to the theory. So the scalar field in some sense counterbalances the Ricci curvature such that you then can build an exact solution. So, and more generally about these mixed scalar f of r theories, that they have such a large configuration space that virtually all metrics can be included, right? So in some sense, there's, you know, for some particular scalar field dynamics, there's a way in which you can get pretty much whatever you want out in this theory. So that's kind of an interesting point from a classical mechanics standpoint, potentially. And furthermore, that astrophysical disturbances can now be, well, I say now be, but there are some difficulties associated with this, but you can, in some sense, self-consistently study the perturbations of this object, right? So if I had these equations, this particular metric, in this particular equations of motion, I can introduce the perturbation on that background and then study how the dynamics would evolve and therefore try to look at perturbations of the metric in some kind of consistent way. As I said, this is non-trivial, and there are some complications associated with this because the solution has got some singular properties to it. I won't really go into much more detail about that, but if anybody's interested, I'm very happy to try to clarify how you could practically try to do this, but there are some challenges. So although you can self-consistently do it in some way, practically maybe it's not entirely straightforward and valuable. So I'm just going to end, I guess, with some general remarks about all this, some philosophical curiosities. So I've only talked about constructing a vacuum solutions, right? I picked some particular metric G and I found that to be a vacuum solution in this particular weird new theory, right? I've engineered a theory in such a way that I can build a G around it, which is a vacuum solution. So what this actually implies is that vacuum gravitational fields in some f of x or mixed scalar f of r theory can imitate the fields of material bodies in a different theory, right? So if I had a matter field neutron star, for example, which cannot be a vacuum solution in GR, I can engineer a scalar field such that this metric that corresponds to that star would be an exact solution in this theory. So this kind of opens up this curious problem about, you know, identifying vacuum from non-vacuum. Of course, in a realistic problem, you have multi-messenger physics, which removes this. You know, and sort of stresses the importance of having multi-messenger physics in particular. If you had only gravitational observations, the kind of existence of theories like this prove that really you can't actually completely determine what theory is underlying it as a result of this kind of inverse existences, right? And vacuum, non-vacuum, and so forth. You need to be careful about exactly tying the metric, which is maybe the only dynamical variable, to the physical properties, material properties. Furthermore, there's kind of a fun problem associated with this, I guess, is that if we studied a perturbation, we could actually find a perturbed geometry such that this perturbation was now an exact solution as well, right? Because I didn't have many conditions on what this G has to be. Basically, what this would mean is if I looked at some deformed Kerr black hole and I perturbed it, there would exist also another kind of f of x or scalar f of r theory such that that metric was now an exact solution. The perturbed metric was an exact solution in some different theory, right? And then you're kind of chasing your tail, perturbing the thing forever, finding a new theory, and maybe it converges, maybe it doesn't, but still is an interesting kind of thought experiment, I guess. Not especially problematic, but still is a philosophical curiosity, as I say. So just some final words that I'll end here with, maybe the next 30 seconds to a minute, is that there are a couple of important points here, right? There may be some mathematical interesting aspects to this theory, but we haven't really talked much about the physical viability. I've kind of given you some hints, maybe, that it's okay with energy momentum conservation. There are some conditions you can impose such that you get rid of ghosts and so on. But it's not obvious whether or not I can actually, reverse engineer the theory around the metric in such a way that I get a theory that's actually self-consistent with other astrophysical experiments. So solar system tests and various other strong field tests all have to be passed, cosmological tests, etc. And if we're only designing a metric or a theory around one of those particular examples, it's possible that the theory that's built will not actually accommodate those other experiments, right? I might not have a consistent cosmology and black hole in the one theory, for example. And also, just to reaffirm some points here, this is not a general solution to the inverse problem, which is kind of the goal we started out with. But unfortunately, doing that in total generality is very difficult. Ideally, you want to find all the theories that you can, that this metric fits, right? But here is just one particular example of a solution to the inverse problem. And whether or not that theory is physical or not remains very up to debate. I certainly wouldn't claim that it's in any sense physically meaningful necessarily, but nevertheless might be a curious tool that could be used in some circumstances. So this is just one particular class of solutions, and there's still a lot of thinking and work to be done on the sort of general inverse problem, both for black holes and cosmology. So I'll end it with that, but thank you very much.
Thanks to you, Arthur. It was a very nice presentation, very interesting topic.
Thank you, you're welcome.
Now it's time for questions. Is there anybody who would like to ask something?
Nicola, I have a quick question. It's
Yes.
Enrico here. So can you go back to the action of the theory you consider this scalar f of r?
Sure. Just give me a second.
Of course.
Yes.
So I'm confused. So as long as you don't couple to matter, why can't you redefine the scalar field to make the kinetic term canonical or standard, so grad phi squared, so as to decrease the number of free functions from 3 to 2? Right, you're always allowed to do that. You just define a new scalar field.
Right. So you mean essentially kill off this V and omega?
Exactly. Yeah. Precisely.
It's a good point. I hadn't really thought about that. You're probably quite right that I think there's some arbitrariness here.
It's okay as long as you don't couple to matter. If you couple conformally to matter, then the free function D or W or whatever reappears in the coupling to matter. Otherwise, you might be able to exploit that freedom if you're in vacuum, at least. So then I have another comment. So you comment about the Bianchi identity, but actually the Bianchi identity comes from diffeomorphism invariance. Right. So actually, even in theories where you don't have the usual Bianchi identity of GR, you do have a generalized Bianchi identity. normally, and you have conservation of the stress energy tensor. It just happens to be the total stress energy tensor of the system, meaning matter plus whatever extra graviton degree of freedom you might have. Well, I guess, well, it's just a comment, but there is no, I don't think there is a compelling reason. I'm sorry, I realized my video is not on. I apologize. Yeah, there is no compelling reason to require that you have the same Bianchi identity as in GR, it seems to me.
Yeah, it's a very good point. So, I mean, you're of course right that the Bianchi identities themselves are geometric invariants that essentially don't care about whatever theory you have, right? They're just properties of manifolds, eventually. And of course, you can have some kind of effective stress energy tensors, as you say, that you can use to then have the same conservation. I guess I was only meaning to say for this particular pure,
of course,
that means. But yes, it's a very good point. Thank you.
No problem. Thanks to you.
Okay. Are there other questions?
Yeah, I have one.
Yes.
Hi, Stefano Liberati. I was noticing again your action. In principle, you know that an F of R theory of gravity can be mapped in a scalar tensor theory of gravity. Metric, if metric F of R basically is a Bronsdicki with omega equals 0. So in a certain sense, what you are taking is F of a generalized F of R, because you can think of a generalization of a F of R theory, given that is mapped in a Bronsdicki with a special potential in something that has two free functions. Because Enrico is right, you can always rescale away one of the free functions that you have. In generalized scalar tensor theory, you can show even the equivalence of Jordan and Einstein frame by the fact that the symmetries of the Lagrangian allows you to pick two or four free functions, because there is an extra one, which is the coupling with matter that you don't have here, of course. So in principle, what you're doing is you're generalizing an F of a generalized F of R, if you like. You can see it this way.
Yeah, right. I mean, so you want to try to include the scalar field so that you can do this conformal business or some ideas.
Yeah, coming to the nature of what you find. I mean, I have a kind of, I don't know if you would call it a philosophical question, but you see, it seems to me that you always have the choice given a metric. You say, okay, this is GR with some maybe exotic matter or strange configuration of matter. It's no more a vacuum solution, this black hole. But, or you can see it as a solution, as you say, of a particular modified theory of gravity. With the problem, as you touch at the end, that you may have several theories of gravity allowing the same solution in principle. It's not that you have any uniqueness, the link is not unique. So I wanted to ask you, I mean, if you see a way concretely at some point, what we need in extra to break this kind of degeneracy? Is it possible that matter would play a role? Because maybe some theories imply some strange coupling with matter, and that you may have some pathologies. I was wondering, what is your point of view about this kind of ambiguity, which is part of this kind of reconstruction?
So there's a lot to unpack in what you've said there, but there's some. So definitely, I talked a little bit about this kind of astrophysical black holes versus some kind of idealized objects. And so, of course, this is also true that I can pick, if I'm allowing for any stress energy tensor that I like, I can also, in GR even, just do the same thing here. I guess this, at least in this context, is trying to really say, well, imagine we really were sure that it was in fact a vacuum black hole that we were looking at. Then we wouldn't want to have extra freedoms that come from the matter sectors. But in truth, of course, there is a degeneracy there that you have to worry about. I think what you would, maybe the way you could try to approach this, more generally, is you would try to pick one of these theories such that, you have some kind of black hole in there that you like, and then try to look at the matter solutions for this. I imagine that would be a very difficult task numerically to do this, but in principle, you could try to study neutron stars in that theory, for example, that emitted these particular objects. And maybe that could give you some insight about exactly how the matter influences. You know, even study the collapse problem, ideally, as well, right? You want to start from some fluid ball collapses, but I don't know.
But it seems very tough to do, right?
Yes,
I mean, I imagine it's going to be very tough.
Absolutely.
Thank you.
Welcome. Thank you.
Okay, I think there is still space for a quick question. Is there anybody? So if no, I would thank Arthur again for his nice presentation.